So far we've looked at nucleophilic addition, a nucleophile attacking a carbonyl group and adding itself to the molecule. You can also have nucleophilic substitutions. When you have a nucleophilic substitution, you have, I'm going to give just a carbon with various substituents, a carbon attached to a heteroatom. And when the nucleophilic and a heteroatom that is more electronegative than carbon, so again you have this separation of charges. So one heteroatom, oxygen, sulfur, nitrogen, attached to the carbon, and this separation of charges, carbon with a partial positive charge. When the nucleophile comes, gets attracted to the partial positive charge of the carbon, and the difference here is that the group that was before, the heteroatom that was before making a bond with the carbon, leaves the molecule and the nucleophile takes its place. So you end up with the carbon with still the 3 substituents that haven't changed, the nucleophile that is now part of the molecule, it has made a bond with that carbon, and whichever heteroatom was before making the bond with the carbon, leaving the molecule, and we call that a leaving group. So here, for example, we've got a bromine atom in an organic compound, and we react that brominated compound, organic compound, with a hydroxyl group, and the hydroxyl group enters the molecule and the bromine leaves as a bromide group. And you can summarize the reaction as you have a nucleophile, you have an organic compound that has an electronegative atom or set of atoms that can act as a leaving group. The reaction takes place, the nucleophile enters the molecule, and the leaving group leaves. Let's have a go at this exercise and see if we can identify the nucleophile, the electrophile, and the leaving group in each of these reactions. And I'm going to do the first one to give you an idea what I'm expecting you to do. So, reaction A. If I look at the structure of the final compound, I can see that I have a chloride ion that is now it's now an independent product, but that was originally part of a structure. It was here. And if I identify the charges in that chloromethane structure, ClCH3, I can see that the chlorine will have a partial negative charge and the carbon will have a partial positive charge. So I can see, hopefully you can see that the substance, the group that is going to leave the molecule is the chloride, the chlorine atom in the form of chloride. So this one is the leaving group. That means there is a molecule entering the structure, and that's going to be the nucleophile. In this case, the nucleophile is going to be the alcohol. Oh, this whole molecule of cyclohexanol. This is going to be the hydroxyl group plus the cyclohexane attached to the hydroxyl group are going to be the nucleophile. It enters the molecule and removes the leaving group. It kicks the leaving group out of the structure. And the electrophile, the one that is needing electrons and the one is needing electronic charge, is going to be that carbon with a partial positive charge. So now I've identified the 3 key players. I've got a nucleophile, which is that oxygen with electrons that are going to be able to donate. I've got the carbon with a partial positive charge, which is the electrophile, and I have the leaving group, in this case the chlorine atom that leaves the molecule as a chloride. So now please stop the video and have a go at reactions B and C. So I hope you stopped the video and had a go at the exercise. The easiest one to identify in reaction, well, B and C, in both cases, is the leaving group, because it's the one that is leaving the molecule. And that will give me an immediate clue of which one is going to be the electrophile, because it's going to be the one the carbon attached to the leaving group. So in this case, the leaving group is this one, the phosphate group. And in this case, the leaving group is the bromide, because I can see here there are the two ions that leave the molecule, that leave the final product. That immediately allows me to identify which one is going to be the electrophile, because the electrophile is going to be the carbon directly attached to that leaving group. So this one and this one are going to be the electrophiles in cases B and C. And that leaves me with which one is the nucleophile. So the nucleophile is going to be the atom or group of atoms that have the electrons to donate. In this case, I have the sulfur that has the electronic pair to donate. Here I've got the nitrogen that has again the electronic pair to donate. So this thiol and this amine are going to be my nucleophiles. Specifically, the sulfur and the nitrogen atoms are going to be the nucleophiles of my reaction, of my two reactions. So what makes a good leaving group? Well, it is important that a leaving group has the ability to leave the molecule. So it is important that that bond between the carbon and the leaving group breaks relatively easily. If not, the leaving group will not leave the molecule. And that is important in both SN1 or SN2 reactions. The leaving group must have a tendency to leave the molecule. When the bond between the carbon and the leaving group breaks, the leaving group goes away with electrons. It takes away the electrons from that bond. So it is important that leaving group is able to stabilize well those electrons, that negative charge. We can look at that breaking of that carbon leaving group bond as a similar way as you will look at the breaking the bond between the hydrogen ion and the counter anion in a typical acid-base reaction. So if you think of an acid-base reaction, you have the bond between, let's say, the hydrogen and the anion, for example, a chlorine, and when it breaks and you liberate the hydrogen ion, you produce the chlorine anion. The weaker the base, the conjugated base, the weaker the basicity properties of the leaving group, the more stable the anion will be, the less tendency will have to attack back the carbon it has just left. So good leaving groups are weak bases. There are atoms or groups of atoms that stabilize well that negative charge, and they will be stable in solution and will not have a tendency to react back with the compound they have just left. A typical example of a leaving group in a typical organic reaction is halogens, chlorides, fluorides, bromides, iodides. However, halides are not are rarely present in biological compounds. So when we're thinking about biological reactions in biochemistry, typical living groups in biochemical reactions will be phosphate groups, the water molecule, alcohols, thiols. Those will be the type of living groups that we find in a biological reaction. In many cases, it is necessary to improve the living group to make it leave the molecule. For example, the hydroxyl ion is not a good living group because it tends to be a strong base. So it tends to react back with the carbon that it has just left. However, when you have a hydroxyl group that has been protonated by the formation and therefore forming a molecule of water, then it's much easier for that living group to leave. So protonating a hydroxyl group forms a very stable living group, which is the molecule of water. It's a neutral molecule, and it will be easier for that molecule of water to leave the structure. In biological reactions, phosphates are common living groups, and they're excellent living groups. And they're excellent living groups because you have the delocalization of the negative charge of the phosphate across the different oxygens that make part of the phosphate group.